Hello and welcome to this presentation on observed changes in flooding across Australia. So in this presentation, I'll mainly focus on two publications. They were published in the Journal of Hydrology last year, and the other was published in Water Resources Research this year. The first focuses on changes in flood magnitude and trying to understand what is driving changes in flood magnitude across Australia. And the second focuses on changes in the flood timing. So in other words, the day of the year that floods occur and what is driving changes in the flood timing, or otherwise called flood seasonality. Now, to start off, I want to present where I'm hoping to take you on this journey with me. So here on the y-axis, I have the trend. So the units are either a percentage or millimeters per decade, depending on the variable. And on the y-axis, we have the recurrence interval, might call it the ARI, in years. And so we're looking at the trend per decade. Well, as expected with climate change, this is on average across Australia, rainfall extremes have been increasing. And so the more rare an event gets, the more likely we are to see an increase. So up to about getting out to the 40-year ARI, we're looking at increases of around 2.5 to 3% per decade in daily extreme rainfalls. However, the stream flow on average across Australia has not been responding the same way as the rainfall has in response to climate change. So below about the 10-year ARI, stream flows have in fact been decreasing historically across Australia, and quite substantially so. And it's only once you get up to about the 40-year ARI, and so really looking at quite extreme events, that we start to see the stream flow trend, an increasing stream flow trend, follow the rainfall trend. So we can talk about it in a different way. Only the most extreme floods are increasing across Australia with climate change, and your more frequent flooding is actually decreasing. And there's sort of a tipping point there where the rainfall trend starts to dominate for ARIs about greater than 10 years. And I hypothesize, and really I want to convince you in this talk, and the main theme of this talk is that it's the role of antecedent moisture conditions that is causing this dichotomous response. So here we have the average trend in the soil moisture. This is in millimeters per decade. And on average across Australia, the antecedent soil moisture, so this is the soil moisture measured or observed rather on the day before the rainfall event occurred, it has on average been decreasing. And these decreases are large enough to offset the increases in extreme rainfalls, resulting in decreased flooding. So that's where I want to go with this presentation in the next sort of half hour to 40 minutes. But I want to take you on a journey in how I got to those results as well. So I'll start from the beginning. Well, really, most climate change studies looking especially at extreme rainfall, they really start from this Clausius-Clapeyron relationship. What this relationship states is, well, if temperatures increase, then the moisture holding capacity of the atmosphere will also increase. That is the saturation vapor pressure. And if this saturation vapor pressure increases, well, and the atmosphere can store more moisture, then if it does rain, and all that rain comes out, well, indeed, there'll be more rainfall and higher extreme rainfall rates. And this rate of increase is generally approximated to something around 6 to 7% per degree Celsius. So we have a really strong physical thermodynamic relationship, which tells us that we expect increases in extreme rainfalls with climate change. So how do we look at this in practice? Well, what we can do is we can plot the observed rainfall against the observed temperature. So here on the x-axis, I have temperature, and let's just pretend for argument's sake that this is the average daily temperature. And on the y-axis, we have the rainfall amount that occurred on that day. And so if we plot our events, they might look something like this. And this is some real data from Sydney. And in this case, these are hourly rainfalls. And if you plot all the rainfall that occurred in that time series, you get something that looks like this, or in fact, exactly like this. So there's a lot of scatter in the data, but what we can do is we can use a technique called Quantile Regression to fit a relationship to the extreme percentiles. And that will look something like this. This relationship between the rainfall and the temperature is generally termed scaling. Essentially, it is just the gradient of that line that was fitted. So what if we do this across Australia, and what results do we get? Well, in this case, we've actually used dew point temperature, which is a more direct measure of the moisture in the atmosphere. And we get the following. So this is for daily rainfalls across Australia. And you can see most of the dots are in that light blue to dark blue category, so in that 5 to 10% range. So yes, indeed, if we look at historical rainfalls and their day-to-day variability, we return a value that is roughly consistent with this Clausius-Clapeyron relationship and confirms that, well, if the day is hotter, we expect more rainfall to be occurring. Interestingly, we can also look at hourly rainfalls. And it turns out that the hourly rainfall scaling shown here are actually higher than the daily rainfall scaling. So a lot more of those dots are dark blue. So we have evidence to suggest that, well, with climate change, or with increased temperatures at least, hourly rainfalls are more likely to intensify than daily rainfalls. Another way of putting this is the shorter the rainfall event, the more likely we are to see it increase with climate change. And so indeed, this paper summarizes that the 99th percentile hourly precipitation sensitivities generally range from 5 to 15%. So this is slightly larger than the Clausius-Clapeyron relationship, but still roughly consistent with it. Although there is evidence again to suggest that, well, maybe sub-daily precipitation extremes are increasing more than the Clausius-Clapeyron relationship. Now, there are other lines of evidence presented particularly for Australia of how rainfall is changing with climate change. Now, this study presented historical trends. And so I will try and summarize their work as best I can. But essentially, they took data from 1966 to 2013, and they split it in two around 1990. And so they looked at the rainfall magnitudes before and the rainfall magnitudes after this split, increasing the event rarities up to a point. So the left panel is the change in the daily rainfall, and the right panel is the change in the hourly rainfall. And the study concluded the magnitude of extreme daily rainfall is increasing in line with Clausius-Clapeyron. It also concluded the hourly rainfall extreme increases are much higher than expected. The lower magnitude shows double the expected rate of increase from Clausius-Clapeyron, while the highest magnitudes reach 3 times the expected rate of change. Now, this depends on what background temperature you pick to use, whether it's a global or a continental scale temperature. But indeed, again, we have evidence which suggests that hourly rainfall extremes are much more likely to intensify than daily rainfall extremes, and possibly up to, well, conservatively, let's say, twice the Clausius-Clapeyron scaling. Now, there's one more line of evidence which we can use, which is climate model studies. Now, this study presents what they call the ensemble mean of the 99th percentile daily rainfall climate scaling rate. So what does this mean? Well, rather than looking at day-to-day variability, as I presented before, this study simulates a future climate and simulates that change in rainfall, and then divides that change in rainfall by the change that was observed in temperature. So it's I guess, a longitudinal division rather than a day-to-day one, if we can think of it like that. And I'll again read their conclusions. So the ensemble mean of the 99th percentile climate scaling over the continent is 5.7%. This is very close to Clausius-Clapeyron. But the strongest extremes, the 99.9th percentile events, scale faster than near-surface water vapor, between 5.7 to 15%, depending on model details. So indeed, now we've got 3 different lines of evidence which all point consistently to the same thing. Increases in extreme rainfall with climate change or increasing temperatures. Sub-daily rainfall is more likely to increase. And the more rare the event is also, the more likely it is to increase, up to about twice Clausius-Clapeyron. And so what can we expect from these increasing rainfalls? Well, indeed, I want to say you can expect increased flooding. So here is a case study for the city of Minneapolis in Minnesota, using a hydrologic and hydraulic swim model. And what was performed in this study was, well, the rainfalls were factored up for climate change, and the temporal patterns were also factored up for climate change. And we have in blue the existing current climate scenarios, and in red we have the future projected. Indeed, the flood levels have all gone up when we project for climate change. So this is just to say, very simply, well, in an urban area, if extreme rainfalls increase, indeed, we expect to see increases in flood levels and flood damage. And this is for an event which was the 50-year rainfall storm. But curiously, if we look at rural areas and we look at the sensitivity between flow now and temperature rather than rainfall, well, we actually don't see uniform positive results. So in this case, red indicates an increase and blue indicates a decrease. And I hope you can see that across the world, generally increased or higher temperatures are actually correlated with decreasing flow. And this somewhat contradicts our expectation that flooding will increase with increased temperatures due to increasing extreme rainfalls. Indeed, an observational study, this was performed by the Bureau of Meteorology, looking at historical trends in the hydrologic reference station catchments, so HRS catchments, finds decreasing trends as well. This study looked at not small events, I guess. This is annual maxima now, and it found pretty much across most of Australia, with the exception of the tropics in the Northern Territory, significant decreasing trends in annual maxima flow. Whereas previously, what I presented was increasing extreme rainfalls. Interestingly enough, if we look at your more common flood events, your more, say, day-to-day flows, well, it turns out that, well, if you look at rainfall corresponding to warmer years and rainfall corresponding to colder years, indeed, on the y-axis we have the cumulative density, and on the x-axis we have the rainfall intensity. Well, yeah, in warmer years, you expect greater extreme rainfall events, and this is consistent with everything that I've presented to this point. But if you look at the resultant flows, well, actually it's only those most extreme events in urban areas that are increasing in response to the increased rainfalls. And even in urban areas where there's a lot of water-sensitive urban design and catchment storage, you can see decreases in the flow depths despite increases in rainfall. So there's something interesting going on here. And this led us to publish this commentary in water resources research. So this was published with Ashish Sharma from the University of New South Wales and Dennis Ledermeyer from the University of California, entitled, "If Precipitation Extremes Are Increasing, Why Aren't Floods?" And the paper essentially argues that this is quite a challenge for the hydrologic community to grapple with, that we don't really completely understand how flooding is changing with climate change. And what this paper postulated was the following. If we have event rarity on the x-axis and we have sensitivity with temperature, consider this perhaps a climate change signal on the y-axis. Well, extreme rainfalls are going to be increasing. And the more rare the event is, the more likely we are to see increases in that rainfall. But floods are not going to respond the same way. And there's some sort of tipping point. So they'll be decreasing below this tipping point and then increasing above this tipping point. But I really wanted to convince myself that this was actually true in the Australian flood data. And so this introduction brings me to this paper where we examined the influence of antecedent moisture conditions and rainfall on flooding and how these are historically changing. So like the Bureau of Meteorology study before, we started with the hydrologic reference station catchments, which are presented here. And for each one of those stations, we cookie cut using the catchment boundaries from GIS. The precipitation, so this is the average catchment precipitation. We also cookie cut the average soil moisture. So this is for the top layer in Aura-L. So the water balance model for all of Australia, which the Bureau of Meteorology operate. And we also cookie cut the, sorry, we didn't cookie cut this. We also took the stream flow from the hydrologic reference stations. And so you can see that, well, there was a lot of rainfall there was some rainfall in June and July, but there was no stream flow response because the soil moisture wasn't wet enough. And then as the soil moisture gradually got wetter and wetter, rainfall was turned into runoff. And so although these three data sets are not completely independent, because Aura-L, the model that generates the soil moisture, is driven by AWAP and calibrated to hydrologic reference station data. In a way, we have these three independent data sources which align really quite well, and this is quite comforting to know, because it suggests that the data quality is very good. What we did was, well, we picked what you'd call equivalent to a partial duration series. We picked, on average, the largest 5 events per year. And importantly, we picked them on rainfall. And so we sampled on rainfall or precipitation. And then we also sample the resultant flood peak that happened after that rainfall. And we also sampled the soil moisture on the day before that rainfall event occurred. So if we take all those events for all those sites and just do a very simple standardization. So we just standardize all those rainfalls and stream flows by the average observed for each of those catchments, we can actually plot a surface of the response. And so this is what I present here. So on the y-axis, we have the peak flow in dimensionless units. And on the x-axis, I have the peak rainfall, also in dimensionless units. And the color or the shading indicates the soil moisture. So brown being dry and blue being more wet. Now, if we look at the bottom left-hand corner, well, if the soil is dry and it rains, you're very unlikely to get much of a catchment response or a streamflow response. But if we look in the top left-hand corner, if the peak rainfall is still relatively low but falls on a very wet catchment, we do indeed get quite a large flow response, and it can be equivalent to the largest flow experience for that site. Moreover, you can see that for the same unit amount of rainfall, you can experience orders of magnitude difference in the stream flow response. So the soil moisture has a huge modulating effect on the resultant stream flow. Now, if we look in the top right corner, well, of course, if you have a very, very large rainfall, it will cause the soil to saturate and you will indeed get a large runoff or a flood. But when the rain falls, it doesn't know the state of soil. So it is a very important thing to consider. Now, this was just looking at the variability, but what we're interested, I guess, is the trend. So this figure presents the trend in the peak flow. Consistent with the study performed by the Bureau of Meteorology, we have decreasing trends exhibited throughout the majority of Australia. So in the southwest, around Perth and Fremantle we have blue, decreasing trends. Around southeast Australia and Victoria, again, decreasing trends. And only in the tropics, maybe around Darwin, is there some evidence of increases in streamflow. So remember, this is a logarithmic scale, but here I am looking at much more frequent events than what the Bureau of Meteorology looked at when they looked at trends. The figure that I presented to you was annual maxima. I'm looking at more frequent events, 5 events per year. So it's probably not very surprising that we're seeing similar trends. But now what happens if I look at the change in the peak rainfall that I've sampled? Again, looking at an average of 5 events per year. Well, the trends are very mixed. I mean, I might argue that there are more, I'd like to argue that there's more statistically significant increasing trends than decreasing trends, but really, at that sampling frequency of that quite relatively frequent event level, there isn't that much trend in the peak rainfall. If I look at the antecedent moisture conditions, well, actually on average, the antecedent moisture conditions are decreasing around Australia. There is evidence for increases in the tropics around, again, the Northern Territory Darwin region. But otherwise, this map, the colours reflect the peak flow colours a lot more, particularly around Southeast Australia, where we have a lot of blue dots indicating decreasing antecedent moisture conditions and indeed decreasing peak flows. Now, of course, I want to comment that we've experienced the millennium drought, so our results are probably quite strongly influenced by the millennium drought in the southeast of Australia. But in the southwest, although the trends in the antecedent moisture conditions are not statistically significant, they are decreasing, and the same can be said of the peak flow. So we can plot all these trends on a scatter plot. So each one of those dots is an individual site, and the colour represents the latitude, so we can have some sort of idea where the site is located. Now, if we look at the top right quadrant, we have these more purplish colours, which suggest, well, the sites are in the northern latitudes around the tropics. And there, the peak rainfall appears to have been increasing, and so the flow has also been increasing. And in the bottom left quadrant, we have the peak flow decreasing as well as the peak rainfall decreasing. But overall, there doesn't seem to be a very strong correlation or relationship with the one-to-one line. In fact, the correlation is quite low, 0.11. But what if we replace on the x-axis the peak rainfall with the soil moisture? Well, immediately the first thing that jumps out is the dots seem to be scattered a lot better around the one-to-one line, and correlation is now 0.48, so it is much higher. And so we can more confidently say where we've experienced increases in soil moisture, there have been increases in the stream flow. Where we've experienced decreases in the soil moisture, there has been decreases in peak flow. But again, we're looking at relatively common events here, events that have occurred on average 5 times per year. What if we look at more extreme events? So now we're sampling on average 1 event per year, something akin to the annual maxima, but not quite, because we've again sampled like a partial duration series. But now the correlation between the peak rainfall and the peak flow is a lot higher. It's actually around 0.5. Another thing that's interesting is that latitude dependence seems to have pretty much diminished at this level of recurrence. So for these more extreme events, we can see that the peak rainfall trend and the peak flow trend follow each other much more closely. When there's increases in peak rainfall, there's increases in peak flow. And when there's decreases in rainfall, there's decreases in flow. But there doesn't seem to be any dependence with latitude. Now the soil moisture trend appears more scattered. There's still a reasonable correlation, 0.3. But indeed now, as we've moved to a more extreme event, it appears that the peak rainfall trend follows the peak flow trend a little bit more closely than the soil moisture trend following the flow trend. Now with this latitude dependence removed, what we did was we pulled all this data together and used quantile regression to try and extrapolate out beyond the 1 year ARI, or the annual recurrence, which is what studies usually look at. And this is where I now come to the plot that I originally presented. On the y-axis, I've got the trend per decade, and on the x-axis, the recurrence or the ARI. And there is a lot of uncertainty around these results, but on average, rainfall has been increasing across Australia. Now, for quite common events, it doesn't seem to be really a strong signal, but once we start moving into more and more extreme events, such as the 1 in 10, 1 in 40, we're quite consistently seeing increases in the extremes. Stream flow, on the other hand, hasn't been increasing on average. So across Australia, for the 2-year, the 5-year event, we're actually seeing on average decreases in that flood. And it's only for the most extreme events up into the 4-year ARI that we see increases. And so only for very, very extreme events are the increases in rainfall translating to increases in flooding. Now, I've tried to convince you that, it's the soil moisture trend that is really causing this to happen. So decreases in soil moisture are modulating the observed increases in extreme rainfalls, causing decreasing in flooding across Australia. Now, just a note, rainfall trends dominate only for rare ARIs. It's one of the take-home messages here. But another note is that, well, if we adopt an extreme rainfall increase of, let's say, 2.5% per decade, And apply this to the average increase of temperatures across Australia of 0.1 to 0.2 degrees per Celsius per decade. The trends presented here correspond to an increase in rainfall intensities of 12 to 25%. So maybe 25% is a bit extreme. Maybe we have experienced larger increases in temperature than 0.1 degree. But previously, most of the evidence that I presented to you was suggesting that it was mainly daily rainfalls that expected to increase in line with Clausius-Clapeyron, and sub-daily rainfalls increase above Clausius-Clapeyron. But actually, this work is suggesting that daily rainfalls might also be increasing above the Clausius-Clapeyron rate of 7% if we are able to look at events that are extreme enough. So I want to draw a line in the sand there on this presentation of this paper in the Journal of Hydrology, and switch tacks now a little bit to look at changes in seasonality or flood timing. Now we use pretty much the same data set, so everything that we've talked about before is still consistent here, and the methodologies are relatively similar, but now we're looking at the day of the year that the floods occur. So again, we're using the same data set as before, the hydrologic reference station. But one thing that is different is now, because we're looking at the day of the year that the flood occurs, we only sample annual maxima, and we sample annual maxima of the precipitation, of the soil moisture, and the stream flow. So no longer are we dictated by when the precipitation occurred, but we're actually looking at annual maxima of the precipitation, the soil moisture, and the stream flow. So the soil moisture is no longer the antecedent soil moisture, but just the maxima. And so this is what a time series looks like. And I want to present this so we can get a feel for what the data actually looks like and what the future, the results that I'm about to present to you, what they actually mean. So this is a time series of the stream flow, the annual maxima flow. And you can see that it's, this is for a catchment in South Australia. And you can see that, well, the catchment is winter dominant. Most of the annual maxima occur around, say, August, September, maybe June, so July, August, September. And the size of the circle indicates the magnitude of the flow. Now, the soil moisture, in this case, also generally is at its maxima around the winter time. And you can see that generally when the flow is larger, the two correspond to each other. So the soil moisture maxima and the flow maxima correspond when the flow is greater. But the rainfall, on the other hand, yes, for the largest events, largest flow events, the rainfall maxima does seem to occur on the same day, or close to it. But a lot of the time, the rainfall maxima can occur a lot earlier in the year, in fact, and so it has a lot more variability. And this spread of when the maxima occur can be measured using a statistic called the resultant length. So I summarize this statistic here. Now, the resultant length for the rainfall is 0.6. The resultant length for the soil moisture is 0.9, and the resultant length for the flow is 0.8. So the larger the number, and the closer the resultant length is to 1, so the closer R is to 1, the more likely that the event occurrence is going to correspond to all occurring on the same day. And the closer it is to 0, the more likely it's actually uniform. So the rainfall is occurring more uniformly throughout the year, the annual maximum rainfall, and so the R is lower. Now I'm going to present the seasonality of all these variables across Australia alongside their R values. On the left-hand panel, we have the seasonality, so the month in which the rainfall maxima generally occur. Now, in the tropics and across a large part of Australia, this happens in February, and this coincides with our expectation. It happens in the wet season. Now, the rainfall maxima tend to occur around southwest Australia around June and July, and around Victoria also around July. However, if we look at the R values and the dots that have a black outline are statistically significant, the R values are very high in the tropics, and we would expect this. Generally, rainfall maxima and rainfall occurs in one season. But around southeast Australia, around Victoria, the rainfall R value is actually quite low, and in fact, it's not even statistically significant in a lot of times. This suggests that, well, although maybe at some stations we have a slight bias towards, in some catchments we have a slight bias towards winter annual maxima in the rainfall, generally the annual maxima can occur at any time of the year. Soil moisture maxima looks quite different. Well, in the tropics, again, we have a bias towards, in this case, the end of summer season. Generally, the maxima occur around, soil moisture maxima occur around March or April. August, September are the months when the maxima occur in southwest Australia. In southeast Australia, the maxima are generally occurring around, looking now, September, October. And if we look on the right-hand panel, the R statistic, well, in the tropics in southwest Australia, the R is quite high, but also around Victoria, the R is now quite high and statistically significant. There's quite a strong seasonality in the soil moisture across Australia, with the exception of some of the East Coast. And lo and behold, the flow actually looks quite similar to the previous result. We have flow maxima occurring in the tropics around March or April, southwest Australia around August. And again, August, September seem to be the months of annual maxima flow around Victoria. And indeed, there's a relatively strong seasonality associated with that, with all those patterns that I just talked about, as suggested by the high R values in the right-hand panel. Now, I've just presented the mean seasonalities, but what we're actually interested in respect to climate change is the trends. So I'll look at Australia in terms of 3 regions. Now, first, let's look at southwest Australia. Well, if we look at the flow, it looks like there is a weak trend towards flow shifting towards later in the year. Each of those dots represent one of the catchments, and the thick line is a moving average for those. And the green line, well, it seems to be shifting a bit later in the season also, but you can see that the soil moisture really corresponds in timing as well, a lot more closely to the flow timing than the rainfall timing. In fact, the rainfall seems to peak a month or two, and the rainfall maxima tends to generally occur a month or two before the soil moisture timing and the flow timing. So it does look like the soil moisture is wetting up, and then we'll have a flood event, an annual maxima occur. And so the soil precedes the flow, and both seem to be shifting in the same direction. Now, for the central north, there is the opposite is sort of true. If we neglect the last couple of years where there isn't as much data and the moving average is biased towards just a few points, we can see that the soil moisture and the flow maxima timing correspond incredibly closely, and they're shifting towards earlier in the year. Indeed, all the 3 lines, the rainfall, the soil moisture, and the flow, I would argue they all look quite similar. So it seems like the entire season is shifting to happening earlier in the year. But still, the rainfall maxima precedes the flow and soil moisture maxima by about a month. So in the southeast of Australia, well, there isn't that much trend in any of the variables. I want to first point out that the rainfall in orange really can occur at any time of the year. So there's no real consistent trend in the moving average there. Now, it may be that the soil moisture and the flow have been trending towards earlier in the year up until the millennium drought, where there appears to have, which is indicated by the grey dotted line, where it appears to be some change occurring. And it does appear that, consistent with other research suggesting that the rainfall runoff relationships in that area have changed with the millennium drought. Indeed, the flood timing appears to have responded quite differently. But in terms of the work that we're doing here, it does seem that the correlation in the trends between the flood timing and the streamflow timing seems to be quite large. So, it can be suggested that the soil moisture and the flow trends are quite well matched. Now, of course, again, we're interested in trends, so I can use this time a circular regression to look at the trends for each of the sites. Now, there's a lot of scatter in these results. Only the north, around tropics in Darwin and southwest Australia, show really spatially coherent trends. And I have to say that none of these trends are actually statistically significant, but there is definitely a trend towards a shift to earlier flooding in the tropics and later flooding in the southwest of Australia. And we're talking about shifts in the order of 5 to 10 days per decade. So quite large shifts. Trends in the southeast of Australia, seem to be mixed. There seems to be a trend to earlier flooding, but again, a lot of variability. The rainfall trends in the tropics and in the southwest of Australia, the colours seem to match the trends in the flow. And now, I wouldn't pay too much attention to the red colours around the southeast of Australia, around Victoria, because remember that the R values there were quite low, so there wasn't any significant seasonality to begin with. The trends were quite uniform, and so any positive trend here is not significant and likely just a statistical artifact of the fitting procedure. But the soil moisture seems to look a little bit more, soil moisture trends seem to look a little bit more like the flow trends. Again, shifts towards earlier soil moisture maxima in the tropics, later soil moisture maxima in the southwest of Australia, and somewhat mixed trends around Victoria. Now, it's hard to really get a strong signal for, or a strong spatially coherent signal for how these things are shifting. So again, we just plot these on scatter plots. Now, on the y-axis on the top panel, I have the rainfall trend, and on the x-axis is the flow trend. Well, yeah, when the rain is shifting to later in the year, which is the top right quadrant, and flow is trending towards later in the year, both sides seem to be shifting in the same direction, or have a trend that has the same sign. And in the bottom left quadrant of that top panel, the rainfall trend is suggesting that we have rainfall maxima occurring earlier in the year, and indeed the flow maxima is also occurring earlier in the year. But there's a lot of scatter, and the correlation is 0.28. So there is some correlation there. But if we replace the rainfall trend with the soil moisture trend, the correlation becomes almost 0.6. It's really quite high. So at the annual maxima level, it is safe to conclude that any changes in the flood timing are much more likely to be driven by changes in the soil moisture timing than the rainfall timing. So with that, I want to conclude and end this presentation. really want to conclude on the point that for more frequent events, it seems that changes in soil moisture are driving the changes in that flooding. But for more extreme events, these are being dominated by changes in rainfall. And so we have a dichotomous response where we have extreme floods increasing, but your more common minor floods actually decreasing. Thank you.